Dragons. I'm Catherine.
I'm Gaurinanda.
And I'm Hrishika.
And we're requesting $500,000 with 5% equity in our company, Q-Charge. Every year, millions of people are diagnosed with cancer. And for them, treatment comes down to a simple but risky idea: burn the tumor without burning the patient. As of now, doctors have a powerful tool to fight cancer in the liver, an electric ablation probe. It works by inserting a small electrode into a tumor and using electrical energy to heat it until cancer cells are destroyed, damaging surrounding healthy tissue in the process.
But here's the problem. The following study was originally designed around a pre-existing simulation technology intended for hepatic tumor ablation. And cancer, unfortunately, doesn't stay in the liver. We now face tumors in skin, lungs, and other tissues with completely different structures and properties. So the issue is, a treatment that works well in one organ may behave completely differently in another. And that can mean either the tumor survives or healthy tissue gets damaged.
So the question we ask is, what implementations need to be done on the device to be able to function on skin, lung, and liver tissues? And what ablative processes eradicate the tumor but also minimize surrounding healthy tissue damage?
This is Eradicate, a precision-engineered dual-heating ablation probe designed for controlled, high-fidelity tumor eradication. Operating within a 6-minute treatment window, it delivers sustained moderate voltage energy to produce uniform thermal profiles while minimizing off-target heating. By accounting for vascular heat sink effects, it ensures consistent, targeted ablation with enhanced precision, safety, and reliability. So our study is based off a pre-existing procedure. This procedure inserts an electric probe through the skin and guides it into the tumor using various imaging sources. Once it's in position, radiofrequency current is applied, which heats up the surrounding tissue and destroys the tumor's cells. The goal of this procedure is not only to treat the tumor, but also obtain a small margin around it to ensure no possibility of future regrowth. Unfortunately, the current RFA model doesn't control heat very well. So instead of just targeting the tumor, it spreads out further than intended, damaging more unnecessary healthy tissue, which can also prolong a patient's recovery time.
The original model comes from a pre-existing ComSol package and represents the body tissue as a large cylinder with a blood vessel and the 4-armed electric probe through it. The model has been changed to include tumor simulation. This includes simulation of a liver, lung, and skin tumor. To simulate tumor ablation, a voltage is applied to the probe, creating an electric field governed by charge conservation. Because the tissue is conductive, this produces joule heating, which becomes the heat source. Temperature is calculated using the bioheat equation, which includes heat conduction and cooling from blood flow, with boundaries fixed at body temperature. To measure actual damage, the model uses the Arrhenius model, which treats cell death like a heat-activated reaction. This gives a damage integral that estimates how much of the tumor becomes necrotic over time.
Our first study was done on a lung carcinoma, which is a type of cancer that forms in lung tissue. Treating it with thermal ablation can be quite challenging because lungs aren't uniform. They contain air spaces and have a lot of blood flow, so heat doesn't spread evenly. Because of this unique physiology, the lung was chosen as our initial test case. In our model, we represented the tumor as a simple sphere and simulate electric heating to perform ablation. We then studied how different factors like voltage, probe placement, and blood vessel proximity affect the treatment. In this study, we analyzed the relationship between applied voltage, treatment time, and the resulting fraction of necrotic tissue. The graph shows that longer treatment times, such as 6 minutes, lead to more complete ablation across a wider range of voltages. For example, around the 20-volt mark, earlier times such as 1.5 minutes and 3 minutes are not fully ablated. However, by 6 minutes, this reaches almost near complete necrosis. This shows that by allowing more time, this enables more uniform heating, reducing the need for higher voltage as a whole, and helps minimize damage to healthy surrounding tissue. When we look at how the damage spreads throughout the healthy tissue, the choice of voltage becomes really clear. At lower voltages such as 15 or 20 volts, the treatment is just not strong enough. It leaves behind the tumor and doesn't hit the minimal requirement for ablation, as you can see on this bottom edge right here. However, on the other hand, 45 volts is too extreme, taking up too much healthy tissue. But at 30 volts, that's when we hit our sweet spot. The tumor is fully ablated with just the right amount of minimal margin into healthy tissue. So overall, 30 volts gives us the best balance between effectiveness and safety. The figure shows our setup where the probe is placed at the center of the tumor. From this setup, we tracked how damage changes over time at 2 points, one closer to the probe and one further away. The graph shows that the closer point reaches full damage faster, while the further point takes a longer time. This shows that the heat is strongest near the probe and spreads outward over time. It also highlights that placing the probe near the center of the tumor results in faster and more complete tumor ablation, making the treatment more effective overall. As a final step, we looked at how nearby blood vessels impact treatment effectiveness through the heat sink effect, since this plays a crucial role in real-world ablation outcomes. Even though the differences are quite subtle, the 20mm case consistently reaches the highest temperatures. This indicates the optimal distance. When vessels are too close, it acts as a heat sink and carries heat away, reducing effectiveness. So around 20mm, that cooling is then minimized, allowing tissues to heat more effectively.
For hepatocellular carcinoma and liver tumor anatomy, this tumor has higher electrical conductivity than the surrounding liver tissue. This allows more current to pass through the tumor, so it heats more efficiently, although the overall heating pattern is still influenced by the probe geometry. In the voltage and 3D damage results, increasing voltage increases joule heating. Around 30 volts was optimal, producing a clear region of full necrosis, with damage of approximately 1. Because the tumor is more conductive, heating is enhanced within the tumor region, while remaining strongest near the electrode arms. For the probe placement plot, the point closer to the probe at x is equal to -4mm reaches full damage faster due to the stronger electric field. For the variable time plot, which measures the fraction of necrotic tissue, in around 6 minutes, this was the most optimal treatment time, showing that at the 6-minute mark, the tumor only needs 20 volts to reach full necrotic tissue ablation. In the blood vessel study, the presence of the vessel introduces some cooling due to blood perfusion, but the effect is relatively small. However, the best result is at 20mm away from the blood vessel.
Now, let's move on to the skin. The tumor in this study is basal cell carcinoma, modeled as an ellipsoid with a radius of 19 mm. First, we studied the effect of varying voltage over a 6-minute treatment using values of 4, 8, 10, 12, and 16 volts. At 10 to 16 volts, the tumor is ablated quickly, but the heat begins to damage the surrounding healthy tissue. At 4 to 8 volts, the heat is insufficient to fully eradicate the tumor, leaving boundary regions untreated and increasing the risk of recurring cancer cells. At 10 volts, the entire tumor undergoes complete necrosis with minimal impact on nearby tissue, making it the most effective voltage over 6 minutes. Next, we examined how damage evolves at 2 points inside the tumor. The point closer to the probe heats rapidly and reaches full necrosis at around 3 minutes, while the outer point heats more gradually but still reaches complete damage. This shows that the probe at -4 is more optimal since it achieves necrosis faster than the other probe. The next study shows the effect of a blood vessel on temperature near the tumor over distances of 10, 20, 30, and 40 millimeters. A vessel closer to the probe, such as at 10 millimeters, significantly suppresses the temperature more than one farther away, like 20 millimeters. Therefore, a blood vessel positioned at 20 millimeters from the tumor minimizes the heat sink effect and allows for more effective thermal treatment. Finally, we studied varying treatment duration. At lower voltages, around 4 to 8 volts, damage builds up slowly and does not reach complete necrosis within 6 minutes. At 10 volts, however, complete necrosis is achieved within the treatment time. From this graph, we concluded that a 6-minute treatment is optimal at 4 volts to 8 volts. Although it takes the full duration to reach complete necrosis, the slower process helps protect healthy tissue while still fully ablating the tumor. Overall, this confirms that a 6-minute treatment at 10 volts fully ablates skin tumor while minimizing unnecessary damage to healthy skin.
Our results confirm two key findings. First, the animations on the screen represent the tissue degradation for each tumor tested.
As predicted through previous graphs, once the voltages reach approximately 30 volts for both liver and lung tumors, regardless of the tumor size and geometry, there is a sufficient amount of margins of tumor degradation. The tumor is fully eradicated, and there is minimal possibility of return from surrounding tumor tissue.
Additionally, the skin required 10 volts to reach sufficient damage to ensure no tumor return. This value is less than the other tumors due to the very nature of skin conductivity because of its proximity to the surface of the body, and is also wet when undergoing testing, which increases conductivity. However, it is in alignment with the other tumors in terms of surrounding tissue degradation.
The second finding was that for a variable voltage and time study, 6 minutes emerged as the optimal ablation window. At 6 minutes, moderate voltages achieved complete tumor ablation that shorter durations simply could not reach.
Running it at 1.5 or 3 minutes required significantly higher voltages to reach the same outcome. A higher voltage means larger, less controlled heat zones that damages healthy tissue beyond the tumor margin. 6 minutes at a moderate voltage is the safer and more targeted approach.
It keeps the localized heating concentrated where it needs to be, while minimizing thermal spread into surrounding healthy tissue. Ultimately, every RFA procedure carries a fundamental balance. There needs to be enough heat to destroy the tumor completely, but too much heat damages the healthy tissue surrounding it.
Our product, Eradicate, is specifically focused on minimizing that healthy tissue degradation. By mapping a cardiac fraction against voltage, time, and vessel distance, we identified the precise parameter window where tumor destruction is complete and healthy tissue degradation is minimized.
There is something, though, to keep in mind. There is a weakness in our studies that come from the initial COMSOL model itself. While we are likening our results to RFA, COMSOL simulation is constrained to a quasi-static version of the RFA, which is joule heating, due to the geometric incapability of the RF module.
Our studies would be similar in RFA, however differ due to the lack of impedance the RFA might face in a real-world setting.
Eradicate is critically beneficial to modern tissue degradation research. By expanding the original electrode's utilization and RFA methods, we made a new type of RFA method that uses the electrode in a specific way for various tumor types, and showed how by using the electrode for only 6 minutes, or a longer continuous heat with lower voltage, we can eradicate the tumor without imposing too much surrounding tissue damage.
So, Dragons, who wants to make a deal?